So in this video we're going to consider the addition of vectors. Okay, so let's first of all imagine a speedboat speeding along the water here, and the speed that it travels at is going to be measured by this arrow here. Now that's a scalar quantity, but the arrow indicates that what we really want is the vector quality, which we call the vector quantity, I should say, which we call velocity. Now velocity has two components. It does have magnitude, giving us its speed, but it also has direction. So we have magnitude and direction. Let's say now that this is the result of two velocities added together. So first of all, there's the velocity that the boat thinks it's going along at. So if I draw that down here, here's the velocity, if you like, that the boat has been instructed to travel at. And you can see it's less than this velocity. The length of the arrow is much less. It's also in a different direction. So what's going on? Well, there's a second velocity, let's say represented by some wind. So the wind also adds to the velocity. It increases the velocity. And so the velocity vector of the wind is given by this arrow here. And so you can see what the wind velocity has done is it's not only increased the magnitude, increased the speed, in this case of the, let's put the boat on there, the speed of the boat, it's also changed its direction. So this is the resultant, and these are the two vectors that added together would give us the boat travelling in this direction and travelling at this speed. In other words, going at this velocity. Okay, so that's the real world example. Let's have a look at mathematics. So let's just draw the first vector. So the first vector we can represent in various different ways. I'm going to just use a column vector. So it's going to go -2 in that direction, and it's going to go down -7. So -2, -7 then. Added to that, we've got this wind vector here, which is quantified as -5 plus 1, -5 and 1 in the positive direction. Okay, so do we just add these two components together? Let's have a go. -2 minus 5, so plus -5 gives us -2 minus 5, in other words -7. And -7 plus 1 will give us -6. And so if we look at our resultant vector, it does indeed go 7 in a negative direction and 6 downwards. So this is the mathematics that we use, this is the method that we use to calculate a resultant vector. So that's with a velocity example. Another example we might think of could be displacement. So let's think of a particle. Let's draw a particle here somewhere. And this time we're going to add several vectors. This time displacement and distance. Now distance is the scalar quantity. So if, for example, I drew a line here, I would say, well, he's travelled in that direction, that distance. It's travelled to there. If we draw another one, to there and to there, then if I'm measuring the distance, it would be the magnitude of these vectors all added together, which would give us a quite long distance. But if we're looking at the vector quantity is displacement. And displacement, as we know, means just how much the particle has moved from its starting point to its finishing point. And so it's this short distance here. So the vector addition of these displacement vectors would be just the resultant that goes across from the start to the finish. So in other words, across here. So again, in the real world example, we've got several vectors added together to give us a resultant going in a very different direction to all the other vectors. Let's see if that works out with the mathematics. So we've got -3, 2 as our first vector. Added to that, we've got 1, 2, our second vector. Our third vector is 6 along and 1 up. Our fourth vector then is -2, -4. So that's the mathematical quantification, if you like, of the displacements that we've got in our diagram. So now let's use the same method as we did before and add these together. So we've got -3. Let's gather together our negatives. -3 minus 2 is -5, and we've got here 6 and 1, so that's 7. So it's 7 minus 5, which is 2. And here we've got 2, 2 and 1 gives us 5, minus 4 gives us +1. So our two components are, the first component is 2, and the second is 1. And this translates to 2 along to the right, and 1 up, which is indeed our resultant vector. So the mathematics here is pretty intuitive, very straightforward. There's just one thing that we need to add to this, which is what would happen if we arranged these vectors in a different order. Now there's only one way we could differently rearrange this, and that's to say we'll swap the vectors around. So if we swapped the vectors around, what would we get? We would have, let's just do the mathematics first, I think. We would have -5 -1 plus -2, -7. Now, of course, just like in ordinary arithmetic, if we're using ordinary arithmetic to add these up, we're going to get exactly the same result. But does that make sense in our real-world example? Well, our first vector would be what? -5, 1. So it's going to go in this direction here, -5 and up 1. So let's draw that in. Okay. And you'll notice that this is exactly parallel because it's the same vector, of course, with this one here. It's just that it's got a different starting point and it ends up over here. Okay, now we've got to draw in -2, -7. So that's going to start here and it's going to go 2 along to the left and 7 down. So let's draw that in now. And that ends up exactly where we expected it to, so at the tip of our velocity vector, our resultant. Okay, so it doesn't matter, it seems, if you start with one vector and go down here and then along here, or you start here and go along here. Either way, you're going to get the same result, the same resultant. And that's because, well, vectors don't have position really. A vector only describes magnitude and direction. So it doesn't matter where you place it. When you add them together, you're going to get the same result. Okay, now have we got the same thing going on here? Let's jumble these up then and check again what's going to happen to our displacement vectors. So maybe if I just swap these around, so I've now got 1, 2 -3, 2, and swap these around as well. So I got -2, -4, and I've got 6, 1. I should really say -2, -4. Makes a bit more sense. The result should again, because the arithmetic tells us that we can easily change the order. It's called commutativity. So we can change the order of our numbers here and we will get the same component in our resultant vector. So the same number here and the same number here as well. So it doesn't matter in ordinary arithmetic if we change the order of the numbers that we're adding together. So is our vectors really commutative like this? Can we change the order in our real world example and still get the same resultant? So all we need to do now is trace our first vector. So we've got 1, 2. So this time we just go along 1 and up 2. So that's going to draw it to here. And then our second vector goes along 3 to the left and then up 2. So it's going to end up here. So what it's made, in fact, is a parallelogram with the first root that we had, but it ends up in the same place. And the same is going to happen with our second two vectors. Let's just check that out. So we've got -2, -4. So again, we're starting here. We're going to go -2 along and 4 down. So our next vector is going to end up there. There we go. And finally, we've got 6 along and 1 up to get us where we should be, to our finishing point there. And so our displacement vector is going to be exactly the same. So we've explored a couple of things in this video. First of all, we've found out how to add vectors together, and it's really very straightforward. We just add the two components. And the second thing is that we've shown that vectors are commutative. So just like in ordinary arithmetic, it doesn't matter what order we add these vectors together in, we can change the order at will and we still get the same resultant. But just before we complete part 1 of this video, let's just consider vector subtraction. What about vector subtraction? Does that follow the same sort of ideas here? Is it just as straightforward? Well, let's redraw this initial vector and have a look at this very quickly. So what have we got here? We've got -2, -7. So -2, -7. It's the same vector as we have before, but I've deliberately drawn it over to one side here, because what's going to happen is we're going to reverse the direction of this vector now when we think about subtraction. Let's just write it out mathematically first, and then you'll see how this works. So if I write subtract this vector that we had here, which was -5, 1. Okay, let's make that minus sign a little clearer. Okay. Now, what we're going to look at here then is whether the graphic, the diagrammatic drawing of our vectors is consistent with our mathematics. So what would we expect with our mathematics? Well, -2 minus -5 is going to give us -2 plus 5, so that's going to give us, the first component is going to be 3, and -7 minus 1 is going to give us -8. Is that what we'd expect? Okay, well, let's have a look at this. We've got to think of this now as -1 multiplying throughout this vector, because what we're doing effectively is scaling by -1. So -1 times -5 is going to give us 5, and -1 times 1 is going to give us -1. So we're going to have 5, -1. In other words, instead of going 5 along in this direction, it's going to go 5 along in this direction, and it's going to go down 1, -1, instead of up 1. So as we saw in the scaling video, this -1 in front of a vector is going to reverse the direction of the vector. So here we've got a vector drawn not in this direction, but now in this direction with the arrowhead at the end here. And that is going to give us a new vector, which starts from here and ends here. So if we draw the resultant, and if we check with our result here, this is indeed 3 along and -8, so 8 down. So that works very nicely. But there's another way of thinking about it, and that would be that if we multiplied this out, so if we had -1 times the -5 and the 1, we could simply write it out as an addition. So we've got -2 minus 7 plus, so we've multiplied the -1 by minus 5 giving us a positive 5, and the negative 1 times the 1 giving us a negative 1. And that will give us the same result, of course. So minus 2 plus 5, in fact the arithmetic is slightly easier here, gives us 3. And minus 7, is that clear? Minus 7 minus 1 gives us minus 8. So just as in ordinary arithmetic, we can take a subtraction sign and turn it into an addition sign. And once we've done that, the mathematics is the same. So we've got now an addition. Just like with arithmetic, we find that vectors are commutative over addition. So they're not commutative over subtraction. So that if you had minus 5, 1, subtract minus 2, minus 7, well, that wouldn't give you the same thing at all. What it would in fact give you is a vector going in the opposite direction. So it would give you minus 3, positive 8, and you might want to try that. But here we've got, we've converted this to an addition, so we can quite happily commute it. So again, we're going to experiment with changing the order. So we've got, let's write it down here, 5 minus 1 as our starting point. So this would give us a vector, if we go back to our diagram, starting here, this will give us a vector going along 5 and down 1, so it should end here. And completing the parallelogram, we've got minus 2, minus 7. So again, if we've got 5 plus minus 2, that's 5 minus 2, giving us 3. And minus 1 plus minus 7, or minus 1 minus 7, gives us negative 8. So again, we've shown the commutative law operates here as well, and we've completed our parallelogram. So now that we've looked at addition and we've looked at scaling, we can finish this video by having a look just at general algebra. So let's just think about this algebraically. In other words, what we've got is any vector A, we've split into its two components. We've called that first component A sub 1, so that's the first a long component. And the second component we're calling A sub 2, so these are just the two components of vector A. And here we've got a second vector, so we're calling it B. B1, B2 are its two components. So we can be given now algebraic expressions, and we should be able to handle those just as we can handle ordinary algebra, as long as we don't get into multiplication and division, where the algebra will be different. But here, when we're just dealing with addition, subtraction and scaling, we can have something like, well, let's just say 2a, and put a line over our vector, so it's definitely two of these vector a's, or a double-sized, if you like, twice a vector, plus 2b. So 2 times our vector b. How would we resolve that? Well, we'd end up with, obviously, 2a1 and 2a2. That's our first step, if you like. And then added to that 2b1 and 2b2. So that's done the scaling. How about the adding together? Well, the adding together is, just as we've seen in the video, very straightforward. 2a1 added to 2b1. And the second component's 2a2 added to 2b2. So, although it looks kind of awkward, looks very mathematical, in fact all we're saying is that we're scaling up those first two components, adding them together, and we get something that looks algebraically like this. Let's do one more. Let's do a subtraction. Say we had 3 A this time, so A, any vector A, subtract, let's just have B, any vector B. What would that look like as algebra? So again, we might want to do our scaling first. We don't have to. We could skip a step, I think, and go straight for this. But let's just do it step by step, nice and easy. Okay, so we've got 3, A1, and we've got 3, A2. So that's sorted out the first set of brackets, the first two components in vector A. So we've now got 3A. And if we're going to subtract, well, what we might want to do here is change this to addition. We don't have to, but it seems to be something we might want to do anyway. Let's just change our vector B then to negative. And all we're doing then is multiplying by -1. So we end up with minus B1 and minus B2. Okay? We could have kept it just as negative, but just to show how this can be changed around, we've done this. We could move, commute these around, but I think what we're going to do now is just add them across. So combine these brackets, so we end up with just one vector. Our resultant vector is going to be then 3A1 plus minus, so minus B1. And the second component is going to be 3A2 minus B2. So that's just a short introduction to vector algebra.